Hello. Oh, that wasn't dramatic enough. Hello. There we go. It's all about the introduction, right? So I had jury duty this week. I was hoping to post these videos before Wednesday, before we had class. And the irony is I could just not cancel class tomorrow, but I'm not going to, so whatever. This is in place of class for this week. I told all of you that we would have a couple of recorded lectures. So here we are. Now, what we have been covering has been a review of systems and controls, okay? This is just taking material from EGR 350, just giving you some backup context, re-reviewing some of the things that you've already dealt with. And some of it is I cover this material slightly different in the two different classes, so I feel like creating some common ground would be a good idea. So what we're going to do is we're going to have ultimately we're going to have a couple of example problems that are going to lead into our discussion on robotics as things progress. So I'm just going to have a couple of examples here. Now what we have is we're going to have a you may recognize this even despite my poor drawing skills. This is an extended forklift, okay? And notice how I drew these linkages as if they were friggin' huge. This is not to scale, nor is this an artistic rendition. And that box, I don't even know what it's supposed to look like, but it's a box, because that's all we need. The idea here is if we wanted to construct this system and control it, it's a forklift, we would have to put in a lot of design work in order to do that. So what kind of design pieces are we going to have to start out with? How are we going to do this analysis? How are we going to put together this? This is clearly a very complex system. If you're a mechanical engineer, if you're a mechanical engineer, the kind of questions that you're probably asking in the design of this system are, how are we going to make the connections? Okay, we're going to make revolute joints, we're going to make ball joints, or is this going to be some kind of a floating rotational joint? Are we going to use ball bearings in these joints? Are we going to use a different type of bearing? Is this going to be a journal bearing? Is it going to be a grease connection bearing? Is this, what kind of connections do we have? As a mechanical engineer, you should be asking that question as far as designing a forklift goes. And specifically what we're looking at, by the way, is designing this aspect here. Okay. Another question a mechanical engineer would ask is, what about stresses? If you understand stresses, what you do is you take your understanding of stresses, you apply it to the individual components, you design how does this component handle the amount of stresses that we expect it to. Whoa, it's super blurry. How do we expect this to handle the amount of stresses that we're going to put on it? How do we make sure that this doesn't buckle under its own weight? That kind of thing. And it becomes a much broader question now of, well, designing the individual components, okay? Here the connection, it's a component. You make sure that the connection itself doesn't fail. You make sure that the components themselves don't fail. You go look at what an electrical engineer would look like. Let's say that this was not a hydraulic, but this was an electric system. You're then looking at motor selection. And I could even put this under mechanical engineer because they will probably have to deal with some motors too. Or they would also have to deal with hydraulics if the hydraulics were used. The electrical engineer would say, okay, what kind of elements of a control system whoa, I keep going in and out of blur. It's pretty fantastic. Wish I could put my camera farther away, but it has to be plugged in, and they don't have an outlet. If I put my hand here, it looks massive. And if you look at this right here, we're dealing with good stuff. I could pick my nose with this finger. Week, 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 week. Yep, you heard that in a senior level college class. Nice. I have no filter. But as an electrical engineer, you're also going to be dealing with a control system. So not only does this have to operate, this has to move, this has to be controllable, it has to have some kind of integrated design that's going to allow you to fine-tune the exact motion of this. A mechanical engineer may be dealing with stability. Here, we're going to be connecting something on here. If you apply any amount of load here, well, anybody who knows physics knows that that's going to create a moment on this end that's rotating the clockwise direction. What are you going to do to prevent this thing from tipping and falling straight down? Well, a lot of times what they'll do is they'll put masses back here, or they'll just put the entire engine to the system on the rear of the vehicle. Sometimes they actually put braces down like this. That's something that a mechanical engineer would deal with probably. Or if you even had a structural engineer, they might deal with that. I suppose the electrical engineer could deal with the bracing, but that's, again, the bracing, part of the bracing comes into what kind of stresses does that incur, and that does tend to be more of a mechanical problem. Electrical engineers not only are going to be dealing with control systems and motors, but they're also going to be dealing with measurement systems. These are all your sensors. Where is the location of this? Where is the piece to this? How do the measurement systems work? How do they integrate with your control systems? How do they connect? You're also going to be dealing with power systems. Okay, we have to deal with a power system. That's just our lives. So there's a lot of different elements of control here. These are vastly different. Calculating the amount of power that's required to lift this is much different than calculating whether or not this beam can handle the kind of load that it's about to undergo. So all of this comes down to this is a very complex design problem. Okay? And you do have to have a good understanding of systems, because quite frankly, these people have to work with these people, or else this thing doesn't happen. If these people work by themselves, you end up with a really good power control system and really good controls system, and this stuff, it might fall apart. The arm bends. Just make it bigger. Well, that changes the control system entirely. It changes the amount of power. You got to work together, okay? And that's one of the beauties of this course, is that we have the ability to take mechanical engineers and electrical engineers, really put them in the same class and say, all right, you guys have to work together on this. You have a design problem that's coming. And you will have a number of design problems that do require a little bit of electrical, a little bit of mechanical. As an electrical engineer and as a mechanical engineer, tough cookies. You're probably going to have to be working together a lot. Anyways, now that we've really talked about the different types of design, we're going to focus on one aspect of design, and it really does impact both disciplines here. And that is, if I load this with a pallet, a box, okay, in its static configuration, I can go ahead and say, well, can each of these components handle this? But what I actually want to know is, let's say this piece here is rigid. And let's say instead of using an electric motor, we actually are using an electric actuator that's a lot like a hydraulic one, okay? In fact, now let's just go ahead and use our hydraulic. We'll say that this is a hydraulic actuator. Okay, it doesn't take away anything that the electrical engineer has to do, because you still have to have hydraulic pumps. There has to be a hydraulic reservoir somewhere. And we'll just say that all of that's on the back end of the vehicle, because that's more than likely where it's going to be. Okay, now the question is, when you do this hydraulic pump or when you do this hydraulic actuator, we can assume here that it takes electric power to run this hydraulic motor. More than likely what you have running your hydraulic motor is actually a firm connection to your gas engine, but I live a life full of whimsy. It can also be powered, not mechanically, but actually electrically. The beauty of this is you identify a power source. You can usually find a way to connect that power source in to derive power and convert it into anything. Here, we're going to be converting that power into hydraulics. Okay. So then what we'll do here is we'll just have a secondary hydraulic motor that comes out and controls the up-down motion of this one. Gives it a little bit extra element of control. Okay, so two hydraulic motors, both of them actuate pistons. These are hydraulic pistons. The pistons move in and out. It gives us the power to lift things. Now the question is, what would the system diagram for the power conversion from going into the motor to being able to lift an item, what does that look like? Okay, so here we're going to start at the very beginning. It's a very good place to start. The ultimate input to what we're going to consider our system is we're going to have some user state the motion that they want. This thing to do. Okay, now it's going to go into here you'll probably have, you know, drawn a joystick. You got some kind of a joystick that's up and down, going to control the up and down of this piece. And if we focus only on one of these motors, like let's say we only focus on this one, then there might be a specific control just for that piece of the arm. I know I've driven an excavator before. They're fun. If you haven't driven one, put it on your bucket list. It's good life experience. But you have one type of control that controls the swing in and out of that arm, because it just, every once in a while, you actually have to be able to control where this arm is without moving this one. It happens. You move them both at the same time, two different switches, but you want to move one at a time. You have the ability to control this. And it comes from a joystick, okay? So the joystick moves up and down. In modern systems, that up and down, what it is it's actually a potentiometer. So this goes into a potentiometer. A potentiometer, what it does is it converts a linear movement into a resistance. So if I push a controller all the way up, the resistance will drop to 0. If I pull the control all the way down, the resistance will go up to its maximum value, which may be anything from 100,000 ohms to 5,000 ohms. There's a broad range of what you can use. Usually it doesn't go above 100,000. Usually it doesn't go below 5,000, because anything below 5,000, it's going to heat up. Anything above 100,000, and you start losing. You start getting inaccuracies in your measurements because you're not getting a high enough current traveling through that circuit to be able to read how much voltage is actually there. Anyways, it goes into a potentiometer. So here, this is a displacement. That's your input. It's displacing how much this piece goes up and down. The output of this is, now the potentiometer outputs a resistance. That resistance gets put into an electrical circuit. And that circuit changes the resistance into an actual power value. This is both a current and a voltage. Okay, that power value, which we could just write an analog voltage. Notice each one of these is actually an element of power, but it's whatever. That voltage then goes into some kind of a controller. and that controller outputs a power, voltage, current. This could be a PWM signal, where a larger PWM signal indicates more power, a smaller PWM signal indicates less power. Regardless, you have some power that comes out of the controller. This power then goes into hydraulic motor. And what happens as a result of the hydraulic motor is you do have to understand a little bit about hydraulics work. Okay, so crash course in hydraulics. If I have a piston tube that is full of some kind of pressurized liquid, hydraulic fluid, and I have some kind of a piston head which sits inside of that cylinder and travels up and down. Okay, the piston head itself has, this is a piston head. It's connected to some kind of a cylinder, moves up and down. The overall force, well, hold on. This is used to create either some compressive or tensive load. The overall force on that piston, if we do a force diagram, the piston inside of the cylinder, sometimes the piston is just a solid rod, which is actually pretty common in hydraulics. You just have a solid rod, and you have this pin connection up here. That's where it's pinned to the arm, and as you push on that, it doesn't move because you also have a pressurized fluid down here, to which that pressurized fluid, it's incompressible, but it exerts a counter force, and that counter force prevents the piston from going down in the cylinder because it would force a certain amount of pressure to be increased in the system. You have a displacement out of here. The displacement of that system, where's that fluid going to go? It would either have to burst out of the system or it'd have to back drive through the motor. So as long as the motor isn't pumping, well, this is maintaining a certain level of pressure, and it can handle shock vibrations. Okay, so what we're going to be doing here in order to control this cylinder's position relative to the piston, I guess, housing, what we're going to be doing is we're going to be controlling the volume of pressurized hydraulic fluid that we have in this chamber. The more volume we have, the higher it goes. The less volume we have, the lower it goes. And the pressurized system, we just have to make sure that the hydraulic system can handle how much pressure it's going to have. So you put pressure-rated hoses, you put pressure-rated valves, you put pressure-rated connections. Make sure that they all match the pressure ratings that we ask of them for these systems. So what the motor is going to do is the motor is going to input electrical power, because that's ultimately where the power source comes from here. A battery or a gas engine with an alternator, something like that. It's going to input this power, and it's going to output a fluid displacement. It's actually going to pump fluid. Okay, now I only write fluid displacement, but really this is a fluid motion power, because this does exist at a certain pressure. There's a certain pressure that is maintained inside of the system. The pump itself is required to operate at a certain pressure. So it operates at a very certain pressure, maintains that pressure. The pressure is ensured to stay there, but when you have fluid displacement in the presence of a pressure, you have power. Okay? When you have a fluid movement, some kilograms per second, you multiply that by a Newton per meter squared. What you end up with is a kilogram Newton per meter squared second, which actually just boils down into Oh no, the volumetric flow rate. My bad. You end up with a Newton meter per second, which a Newton meter is a unit of energy, and a Newton meter per second is a unit of power, because energy, if you take the derivative of energy, you get power. So this is power. It's just fluid power. You have a fluid displacement operating at a certain pressure level. Okay, so here you have a certain amount of power that's coming out of the motor that goes into the cylinder. Okay, the cylinder then converts the fluid displacement at the certain pressure into a linear displacement. Okay, now this linear displacement is occurring in the presence of a force. Force times displacement is equal to energy. So we could also say a linear velocity. That's something else, because a fluid displacement is going to cause a velocity out of this component, which then is a direct transfer of power. However, the linear displacement is probably easier to understand. You extend it, you contract it. But do know that this is actually a function. Okay, so that linear displacement then goes into a lever. Here, this is a lever based on the orientation of how this is constructed. A certain amount of force on this is going to cause a certain amount of displacement here. Okay, so it goes into a lever, and that lever converts a linear displacement into an angular rotation. And here I'm going to have to start going down because I am at the end of my board. But it goes into an angular displacement, which causes the rotation. Okay? Now that angular displacement then goes into the cargo, which would be at the very end here. It is rotating up and down. And what you have is cargo movement. Okay? Which is the output of the system. So really, there's a lot of components that have to go into this overall block diagram. Just to extend this arm, just to rotate it out, it starts with somebody indicating, which is the initiation for the control system. Here, this is an open loop control system. We don't have any feedback. Okay, if this hydraulic thing breaks, it's going to keep shooting hydraulic fluid because it has no idea that there's a problem. We have no feedback here at all. Okay, a very rudimentary system, if you ask me. Not only that, but this system itself has no idea of understanding whether or not it's doing a good job. So if this thing is tilted at 30 degrees, it'll behave the same way. If it's tilted at 90 degrees, it doesn't care. It doesn't care if the cargo falls off. There's no way of knowing that cargo movement, whether or not it's suddenly dropped to zero because a piece in this chain has broken. It doesn't know it. You can still move that potentiometer, that cuckoo, you can still move it the same amount. So this is a control system. It is. The idea here is that there is a feigned feedback loop that goes like this, where you're watching with your eyes where the cargo is, and that causes you to change your own movements to change what that controller is receiving, okay? And that becomes a feedback loop. It is still an open loop because anytime you require the person to themselves be the operator, there's no element of actual control over that. You have somebody who's not trained, they're going to be launching this thing and they don't know themselves how to do it right. So this isn't a real closed loop control system, but it's how we take an open loop control system and recognize that there is an element of feedback there. Okay. So as far as developing the power calculations, the beauty of this is there's going to be certain losses at every location. Okay. Here, the potentiometer, this is a direct translation between displacement and resistance. This is a direct translation between resistance and voltage. We don't lose, we may have a little bit of error and accuracy in each of these, You know, the error here may be actually on the order of several thousandths of a percent. You can get some really, really high quality potentiometers that can detect very fine movement. However, if you can take this controller and you can jiggle it by 5 or 10 degrees, and it still registers the same potentiometer resistance reading, then your error begins increasing substantially. And then you may be dealing with 1 to 5% error. Okay, and so error is introduced in every single aspect of this entire system. It is, unfortunately. And so even though, yeah, you may design this, you may control this, not only are we introducing error, but we're also losing power. There's some inefficiencies, some pieces where power input into the system is going to be converted into heat. Okay, so here we convert this into voltage. Voltage goes into the controller. The controller itself uses some amount of power. It has to. The circuit itself uses some amount of power, also has to. Although we can really minimize the circuit power usage just by having smart resistance placements and using minimal amounts of components and using the right components. So we can minimize the power consumption here, power losses. We can also minimize the error here by making sure that our circuit is very simple, straightforward. Okay, so at each step of here, though, there is going to be power losses. You know, as you convert power goes into the motor, well, the motor is not 100% efficient. Some of that power is going to be converted into heat. Okay, not all of it's going to be converted into fluid displacement. So here we may have an efficiency of 0.8. Okay, and we may have an error where it incorrectly transmits the amount of power. This one's probably going to be really small. I would put this maybe. It's just very small. You put in more power, you're going to get more displacement out of it. Okay, there may be a latency involved. Latency is another variable you could include here. Latency. But that's just how responsive it is. Once it experiences that power, how long does it take for it to move that fluid? If I push up on the controller and it takes 5 seconds for this thing to move up, it's going to feel like forever. If I push up on this controller and this thing moves up immediately, there's no latency, a very, very small amount of latency. So you can see already we're getting into efficiency. This is power conversion. We're getting into error. This is information conversion. We're getting into latency. This is time conversion. We're now not just dealing with one single aspect that we're looking at, forces, stresses. We're now looking at how everything interacts and how all of these pieces together, the cumulative error that starts here and ends here, that's the cumulative error from when I push up on the control stick to when this thing is actually in the position that it is. There's an error associated with that. If I say, you know, if I just mark on here like this is at 5 feet and I push it up to 5 feet, I may be getting anywhere from 4.8 to 6 feet. That's the error. Okay? Similarly, when I say push up on this, I'm going to cause a certain amount of power to be pulled out of a power source, maybe a battery. Okay? And that power draw from the battery, that's not going to be equal to the amount of power that's being used here because we have inefficiencies. We have power losses in the motor. We have power losses in the cylinder. There's going to be a small amount of eddy currents that form inside of that cylinder. You're going to have some power losses because, quite frankly, some of the power that's coming out of this is going to go into stressing this member. Stress is given by a strain multiplied by a stress. There's going to be a small amount of strain and stress induced in this member because you're putting it in tension. There's no way you can do this without putting it in tension. You you have a beam that looks like this. Your input load is here, your output load is here, and then this experiences a force in that direction. You're going to be using some of this to create a horizontal load that has nothing to do with the output power. It's a different direction from the output power directly. So there are power losses, there are error losses, there are latency issues, there are some issues with resolution, there are some issues with accuracy, all of that, a lot of that goes back into the error. This system as a whole is very complex. And what we can do is we can identify the relationships between each of them, okay? So the potentiometer, the resistance that comes out of the potentiometer, the relationship here is you're going to have some resistance value is equal to some linear factor of the amount of distance that the controller moves. So maybe I'll put omega for whatever the resistance per distance is, and then L will be however far I push that controller. So that would be the relationship between the output and the input here. This is the transfer function, ultimately. Resistance to voltage, depending on the circuit you do, you may be able to get a perfect one-to-one ratio. The voltage is equal to some multiplying factor, which I'm going to call C, times R. So here you have a transfer function that is perfectly linear. That's actually a really great transfer function to have. Linear transfer function, there's a very little amount of error. There's no latency. It's just perfect. Okay. This goes into the controller. Now there's going to be a very, very complex difference between the voltage readings going to the controller and then the power being sent out by the controller. This isn't going to be instantaneous. Because this does usually require some amount of programming or some amount of computing, there's always going to have to be a time gap where those computations have to happen. Computations have to happen in a finite amount of time. It's not an infinitesimally small amount of time. It is actually finite. We can measure the amount of time that it takes to perform the calculations needed to convert a voltage into a power source. Okay? This is one area where microcontrollers actually do let you down because microcontrollers introduce latency. But I digress there. So as we continue to progress through all of these different system components, we can develop the transfer functions, we can figure out what the power transfer coefficients are, we can figure out what the error associated with it is. The information coming out versus the information coming in, how likely is it that they're going to land in the same place every time? How likely is it that the information coming out is going to be exactly what you want it to be as opposed to what it actually is? What's the difference between the actual output and the theoretical desired output? Okay, that's your error. And the latency is there's just going to take a certain amount of time. So really this problem becomes much, much more complex than just simply looking at here's the mechanical engineering components, here's the electrical engineering components. Because now here are the transfer functions, which by the way the transfer functions can be useful for identifying power conversion, can also be useful for identifying latency, sometimes error, but most of the time it's used for converting power in between these different facets. Okay, how does power flow? And our transfer functions give us that information. So tons of information on every single block in this block diagram. And I hope that you can see here just looking at this, all it is it's power conversion. Power is being converted from one entity to another. Systems and controls is all about power conversion. How do we convert that power? Once that power has been converted, once it's been converted from an electric power to a hydraulic power, from a hydraulic power to linear displacement power, from linear displacement power into angular power, I mean, that's a lot of different power conversions. How does that work? A good systems and controls analyst will be able to identify the physics relationships involved in each one of these. Which means this is physics 1, this here is physics 1, this here, fluid dynamics maybe, maybe thermodynamics, maybe physics 1. This here, maybe physics 1, maybe fluid dynamics, maybe energy systems. This here, maybe microcontroller design, maybe circuit design, maybe electronics design. Here, this is all electronics design. There's so many facets here. You got to work together. You have to be able to, if you wanted to design this entire thing by yourself, you have to understand every one of those areas of engineering and physics. So, fun example problem that really kind of shows the complexity of the problems that we're dealing with. I'm going to give you another example problem over a different type of system. I'm probably going to record it tomorrow. We won't have class tomorrow. I'm going to give you a recording instead. Tomorrow, ironically. But yeah, so there's a reading assignment that's been posted. I'm planning on posting another reading assignment. Good luck.